Hello, this is Max and welcome on DDSR programming channel. Today we will talk about R optimization. So our dataset can be represented as a network, and this is a subset of our dataset. The darker blue nodes are associated to a viewer, and the lighter, smaller nodes are associated to a movie. We will compute the coupling between each viewer. And so what I mean by coupling is how many movies they have seen or they have watched in common. And so the end goal is to get a data frame where we have, let's say, viewer ID 3 in one column, then viewer ID 0 in the next column, and then a value of 2 in the third column because they have watched 2 movies in common. So that's it for the dataset. Let's look at the first implementation of this algorithm, and it's going to be the simplest way that we could code it. We basically just do 2 double loops. What happens in R, and the reason that this is slow and bad, is that R kind of find a place in your memory on your computer to put viewer coupling in, but doesn't take into account that it might grow. And so if you start growing it, at some point you will run out of space of the slot that was assigned for this data structure. And then if you run out of space, what it has to do is that it will take it and recopy it somewhere else. And that read and copy takes time. So this is where you can lose some of the performance. This is done. It took 95 seconds. So one of the reasons it took so long is that we were growing viewer coupling here. What it means is that viewer coupling at the first step was of length 0, and then each time we found a pair, we grew viewer coupling. Often it's hard to estimate exactly how big is going to be your final data frame, but you can have a pretty good idea. And so what you will do is that you will define it bigger than what you need and just cut it in the end when you actually know how big you ended up being. And so we will copy this to the next section, and this is when we pre-allocate the data frame, but we don't do any algorithmic optimization yet. And a heuristic we can use here is if we were creating a vector that is of length equal to the number of rows we have in our data frame time something like the expected amount of pairs that each viewer gonna get. It turns out that it took 86 seconds. The difference in time, as you saw, is mostly because we're now not growing the data frame, but we are predefining it. We could probably have been a bit faster if we had chosen a smaller size that is still big enough. This just shows you that pre-allocating your vectors, data frame, data structure is gonna save you some time. Other than pre-allocating, another thing we can do in R is vectorizing. Vectorizing an algorithm is often hard, kind of like, reasoning about it. It will make your code maybe a bit more complicated, and reasoning about it will be harder. In R basically means that we will do operation where instead of using a for loop, it will go through each calculation or each element kind of by default because the function is already vectorized. And so what this means is that usually in R, if you use a function from base R, a function from that comes with R, those functions in the back, they will go and do a for loop, but they will do it in a language where the for loop is not costly. So they will do it in C++ or Fortran, and so you will get all the speed you need there using the for loop over there. If you use the for loop kind of in the front in R, then it's going to be very slow. So is it going to be faster than 86 seconds? Oh, by much. So now it took only 6 seconds. And you see that we have most gain when we used vectorized function. You might wonder why we gain so much if we have still used 2 for loops. And this is because our for loops here are doing much less work, and most of the work is being done within the split, within the combine. And then we are using a list, which is maybe more appropriate to store and kind of increase or aggregate our results. And then when we bring that down or retransform it into a data frame, we again use vectorized function in R. So string split and names, we just give one function and one list, and it loops through the list to get the names. we give those names as a vector, and then with string split it goes through this list to split it, and on and on. So all those vections are vectorized, and that's why we go much faster. The next way we will try is by using some linear algebra, and usually in R, linear algebra is quite optimized, and so maybe we will go even faster than 6 seconds. So the trick will be to do a matrix multiplication, and so we need to transform our data, or data frame, to get a matrix, and we will do a matrix multiplied by a transpose of that matrix, and so this means that the columns and the rows are interchanged. And a way that I like to use to create the matrix from a data frame is to transform all of our IDs, so the viewer IDs and the movie IDs, to indexes for the matrix. And so this, I mean that let's say we had viewer IDs that were actually names of people. One way that we can transform that into indexes in R in a kind of a fast way is by first using the asFactor function, and factor will give a dummy variable or an integer to each level in our vector, and so in this case each level will be each unique viewer ID or viewer. And so if we want to get those numbers out after, we can use the asInteger function. And so by getting our vector, passing it to asFactor, and then passing it to asInteger, we will get numbers of 1 to the number of unique ID we have. And so in this way we can just say, you know, the one that has the number 1, now those data points, they go at the first row of our matrix, second row, third row for the other IDs. And then if we do the same for movie IDs, we will create a matrix that has the viewer IDs and then the movie IDs, and we will just put a number 1. We will fill that up with zeros, and we'll put a number 1 when we had a match between the viewer ID and the movie ID. And then we will transpose that matrix and then do the multiplication of that, and so it will result in a table that is viewer ID by viewer ID, and the number will be the sum of time that they had movie IDs in common. And then we will retransform that matrix into a data frame. And so basically we will just take all of those pairs and put that into a long data frame, and then we'll filter that data frame to keep only the instance where viewer coupling is not 0. Tick-tock. And moments of truth. Oh my god, this was fast. So this took 0.05 seconds, and previously it took us 6 seconds, and so this is 6 divided by 0.005. This is 120 times faster than kind of a good, you know, a decent way to code it in base R, and it's way faster than, you know, the most intuitive and kind of shorter way to code it, which is actually, let's calculate that, it's actually almost 2,000 times faster than the first way that we tried. And yes, this is a bit more complicated, but it's mainly because we didn't get the data in the right shape. So our data were in a data frame format, and most of our code was actually just to transform it into a matrix. And so that was this here, and then it was this here to get it back. The actual computation was all done into the matrix multiplication operator. And so this is it for linear algebra. It's quite good. Now there are two other ways that we can do this, and you'll see this code is very, very short, which would be a plus for those packages. And it's by using the package dplyr or the package datatable. They are both implemented in C, and they both received quite a bit of effort to optimize them. Datatable is very famous to be the fastest library, or one of the fastest library to do any data transformation when you're kind of data frame oriented. And dplyr is quite fast, but they are better known for how easy they are to code and to interact with. And we actually did a whole playlist on dplyr that you can get by clicking here. Okay, so in dplyr, in the kind of the data frame format, the way we will approach this is that we will join our df, the data frame with the movie viewers and the movie IDs. We will join on itself. So we have here, let's say we have our viewers and our IDs, and then so we will double that table and bring it here and find every places that movie IDs are equal, and then duplicate those two rows, and then we'll do some filtering and some aggregation. And let's run it. And this was taking 0.0567 seconds. Okay, so it is a bit faster. It's about twice as fast as the approach by linear algebra. Okay, so still twice as fast. Are we gonna get even faster with datatable? And my guess is that we will. Datatable kind of breaks a rule in R. Usually in R, almost every function that you apply, they don't transform your data that you gave in. They will just return the same data frame that was transformed, and if you want to overwrite it or save it over the same variable, you will just do the arrow, and like let's say I wanted to have saved that over as data frame again, as df again, I would have written df here. But in the case of datatable, it does what it's called in place change, and so it goes in the same place in the memory of the computer and modifies the data frame there, and your variable in R, they point to that place, and whatever is done to the actual element that is referred to, R is not doesn't know about it or doesn't care about it. It just returns what's there, and datatable will go and just change these things. And so it saves, it makes it faster because it doesn't have to copy the data and then put them back in a different place, but it also makes it easier to work with a big data frame in R, because let's say that you have 60 gigabytes of RAM and you have a data frame of 7 gigabytes. You're basically almost maxing your RAM already, because if you want to do any transformation of it, you need to copy the whole data frame onto another place, and then once you're done copying, you delete the previous version. So you need to first double your RAM before you can rename or overwrite one data frame. In datatable, you don't have to do that because it has this in-place transformation. And so that's it. Let's look at it and time it. Okay, you ready? How long is it gonna take? And 0.017 seconds. And this is a little bit, almost twice as fast as dplyr. And so in this case, we're talking about very, very small gain. But you know, if it was going to take a day, well, now it's just half a day, and when you're starting to think in these scales, just twice as fast is quite a big difference. So it depends what you need, and it depends what's the problem at hand. Now let's do a general comparison. One thing to note is that depending on your data, each algorithm won't perform exactly the same, and I can illustrate that by regenerating a new random data set where we actually make those data points even bigger, and we will see the difference or how each algorithm scale with the data frame size. And so we will make it 2 times bigger and see how does this affect the scaling of our different algorithms. So let's run this. So it just finished, and we can see that actually this time it's the approach by linear algebra that is the fastest, and followed by datatable, followed by dplyr, and then all these approaches are 18,000 times faster. And so we see that the worse algorithm scale even worse as we get more data points. And we also see that there are three best approaches, so the linear algebra, dplyr, and datatable, are quite equivalent in this case. Here you have it. How can you make your code 18,000 times faster? Well, do not do a for loop and grow a dataset. This is not the way to go. You should probably either do some linear algebra or use dplyr or datatable. If you are optimizing your code too early, you will waste your time, or you will make your code be much harder to maintain and harder to read. And yeah, so early optimization is often a problem, and also maybe misdirected optimization. So it's very important usually to measure your code and which part of your code are very slow, and so then you can optimize only one part. So imagine that in this case, this algorithm of counting the viewer coupling was only one part of a big function or a big program. But then I would have calculated the time it takes to run every chunk of my program, and then I would have identified probably that this viewer coupling computation is very slow if I had used the first version of it, and then I would have started to optimize it. When you optimize for speed, sometimes you will change algorithms that are worse for memory, and so you have to consider that trade-off, and are harder to maintain and understand, or sometimes you will bring dependencies and other packages, and that can make your code sometimes a bit more fragile in the long term if it's a library that is likely to be deprecated or not maintained anymore, or things like that. So those are a few things to keep in mind when you do optimization. And otherwise, stay tuned and come back next week for Julia and our videos. So in the next video, we will see if we can make our R code much faster by implementing the maybe crucial or slow parts of R into Julia. If you enjoyed the video, please like and subscribe. Thank you for watching, and see you next time.